Good afternoon. This is Senior Design Team S1 from FIU's BME department. We're going to be presenting about our senior design project, where we designed and fabricated an intraocular phototherapeutic implant for diabetic retinopathy. I'm going to hand it off to Sujana so she can start us out with the background.
Thank you, Johan. So I'm going to start off with the pathophysiology of diabetic retinopathy. So the common cause is high blood sugar levels or hyperglycemia. And although there are multiple outcomes, our focus is retinal hypoxia, which is low oxygen consumption by the retina, leading to retinal neovascularization. Given that, we know during sleep, dark current leads to a large amount of oxygen consumption in retinal rod cells. Light adapting the rods during sleep shows to decrease oxygen consumption in the eye. Next slide, please. Moving on with the clinical need, according to a 59 population-based study in 2021, 103.12 million adults suffer from diabetic retinopathy, and this number is going to drastically increase by 2045. Next slide. Diabetic retinopathy is the fifth leading cause of preventable blindness among diabetic patients with the ages of 50 years and over. Unfortunately, the current treatment modalities present are prone to low patient noncompliance and require multiple revisits for treatment. Next slide. So some of the examples of these current modalities are your intravitreal anti-VEGF injection and the panretinal photocoagulation. Although both does decrease macular edema, a common symptom of diabetic retinopathy, and does improve vision, they're both invasive, require multiple revisits, and leads to further risk of eye damage. And lastly, the last current modality is contact lenses. This one is non-invasive and long-lasting. However, the patient still has to have a daily manual insertion and removal of these lenses, which can further risk corneal abrasion. There's also another risk of broken tritium leakage, which can provide high radiation dosage to the patient's eye. Next slide. Next, you have the business need. So this table summarizes all the current modalities and the cost over a 5-year and 10-year period. So as you can see at the bottom, the implant has a drastically lower price compared to the current modalities with at least $4,000 US. In addition, there are follow-up surgery costs, but this would be approximately over 14 years after insertion of the implant. I'll now pass it over to Johan, who will start us out with the project scope.
Thanks, Rajana. So when it comes to the project scope, we decided to very carefully balance this because we got a lot of feedback in our first semester, given that we were reaching for the stars in trying to do all sorts of things like packaging and getting the device ready for commercialization. So given that we wanted to deliver a quality project, we decided to show proof of concept that we can make a light-emitting implantable device for the eye. So that was our minimum viable prototype. And given that, we received a budget from the sponsor at $300 and that we estimated completion at around July 2023. So when it came to deciding how we were going to illuminate the retina from an implant, we considered various light sources. The 3 out of these 4 are optoelectronic, those being the lithium battery, photovoltaic, and magnetoelectric, which all convert some type of material into, or some type of input into an electrical signal that will power a circuit. And then there's a phosphorescent light source, which would use a chemical process to emit light. So in the end, we found that the one that meets our 3 criteria, being power density, lifespan, and miniaturization potential, is a magnetoelectric and multiferroic power source, as it can last indefinitely as long as it's not damaged, and can deliver a lot of voltage and current relative to its size. So in designing the implant, we decided to be very robust in terms of our preparation. So we have around 9 or 10 marker requirements and corresponding design inputs. However, we're only testing 3 of these within the scope of this project, given budget and time. The first of these is number 3, which is that the implant must provide a light dose between 490 nanometers and 530 nanometers in wavelength. This is because the maximum irradiance of the retinal rod cells is, maximum absorption of the retinal rod cells is 498 nanometers, which is well within this range. The next one is marker requirement 4, which is that the implant must provide a light dose between a photon flux of 30 to 1,044 photons per micron squared per second for 365,000 8-hour intervals, which is 365,000 full hours of sleep, about the amount that a human gets for the course of their lifetime. This is a light dose that is endoscopic field of vision. That way it doesn't hyperpolarize the cone cells of the eye and wake the patient up, but it's still high enough in photon flux to hyperpolarize the rod cells and light adapt the eye. Marker requirement in design input number 6 is that the implant must not reach temperatures above 38.5 degrees Celsius in situ, which is 1 degree above homeostatic body temperature, to avoid burning any surrounding tissue. Here's some more design inputs and marker requirements. This is a list of various standards that are relevant to the device. We mainly focused on biocompatibility and implantability and the surgical procedure that would go into implanting and using this device. So this is our design concept that we ended up landing on. It's a integrated circuit for rectification and illumination that's mated to a magnetoelectric assembly. This magnetoelectric assembly that you can see is a piezoelectric fiber that is mated and coupled to a magnetostrictive foil in parallel. And then these are mated by solder through electrodes on the piezo fiber and the rectifier circuit via solder. So when it came to the working concept of the device, to kind of explain it quickly, you have external input coils, one being AC and one being DC, that provide an AC field and a DC magnetic field to the device. Now, magnetic fields can permeate all tissue with no problem or impedance, which is really useful for this application and why we use the magnetoelectric implant. So we'll apply requisite kilohertz level AC and DC field that will resonate with the magnetostrictive foil, and that will provide a mechanical load on the piezoelectric fiber, therefore providing a AC voltage that is then rectified by the rectifier circuit and fed to the LED, illuminating it and light adapting the photoreceptor cells of the eye. So as described earlier, you can see that for our integrated circuit, solder was used after using lithographic techniques to develop the PCB and put all the on-chip components on there. And then materials like commercially available epoxies were used to make the different layers of the magnetoelectric power receiver. I'll hand it off to Christina to discuss simulations and verification tests.
Thank you, Johan. So the first simulation done was on multisim to ensure that our proposed circuit worked. On the left-hand side, before the simulation is run, you can see the LED off, and then after the simulation is run, you can see the light turned on. Next slide, please. This is our temperature simulation. The above signifies, well, the temperature, and below it's the heat flux. So you can see that the circuit did have some heat flux, but it still was not enough to cause a temperature change in the tissue. Next slide, please. This was the first verification test performed, spectral characterization. It was performed using a spectrometer and integrating sphere. The spectral graph obtained contained two peaks, which was expected since it's a cyan color, which contains both blue and green light. It also passed the acceptance criteria as one of the peaks was at 519 nanometers. Next slide, please. After we did a transmissivity protocol, this used a Gauss meter to measure the DC field and then a photometer to record watts. The watts were then converted to number of photons and they were plotted against each other, photons per micron versus DC field in Gauss. So you can see that there is an optimum. However, we would not be using the optimum as it produces too many photons outside of our accepted criteria. We'll therefore stick with the DC field that produced photons in the lower tail of the graph, the left-hand side. And because it's a lower DC field, it also leads to lower power consumption. Next slide, please. So this was our temperature verification. One of the thermocouples was inserted into porcine tissue by itself, and another of the thermocouples was inserted to porcine tissue that was surrounded over the circuit. So because both of them behave the same way, we can conclude that the LED did not contribute to any temperature changes. However, what was unexpected was that it showed a drastic temperature decrease within the frame of only 30 minutes. This could signify that the porcine tissue with its high thermal conductivity was just equilibrating to the surrounding temperature. To prevent this, we can redesign the protocol to keep the porcine tissue at body temperature and then probably have like lamps or hot plates to keep it at that temperature so we don't see this drastic decrease. I'll now pass it over to Jafti to discuss global awareness.
Thank you, Christina. For global awareness, we want to consider that over 102 million of adults are suffering from diabetic retinopathy. And for the current treatments and current modalities that incur ongoing costs, which is VEGF injection and photocoagulation. And members of this population will pay high amount of money for the rest of their life just to get treatment for that. Next slide, please. And over 800 million of people in the world will spend about 10% of their income just in healthcare expenses. And that will limit their ability to pay for food, for education, and other necessities. And a lot of them cannot spend that money just on treatments. And if diabetic retinopathy left untreated, that would cause a lot of those people who suffer from that disease that will lead to blindness. Next slide, please. The number of adults with diabetic retinopathy will increase to 160.50 million of people by 2025. That increment is about 60%. And optoelectronic ocular photograph's competitive advantage in the marketplace is its relative permanence when compared to current modalities. Next slide. For future work, this is a wireless multiphysic power delivery, and that has many applications to consider. For example, neurosimulation, cardiac conduction, and neurosensors. So the current project requires the development of fixation features, further miniaturization, magnetic coil refinement, and also the consultation of ophthalmologists for surgical procedures. Now I'm going to pass it over to Johan for patents and acknowledgements.
Thanks a lot, Jeff T. So when it came to considering the commercialization and eventual sale of this device, a patent would be necessary. So we did a lot of research on competing or related patents. One of those being the radioluminescent contact lenses described before. The main similarity here would be that they would be a competitor, but the use and technology used is totally different. So from a patent standpoint, that would not offer a huge challenge. There's another one about controllable ocular phototherapy. The main relation here would be that it's implanted in a similar location, either under the eyelid or in the posterior portion of the orbit. However, ours uses magnetoelectric induction to work. There is no claim laid on that by the second patent. And lastly, there's a 3-coil wireless power transfer system for eye implants that does use magnetoelectric induction, but that's in the form factor of a lens that's implanted behind the cornea. So again, ours is like the inverse of the last 2 patents, essentially. So we'd have to leverage the use of the magnetoelectric effect, as well as the ubication of this in the orbit and eye anatomy to successfully patent it and lay claim. Lastly, we'd like to acknowledge many people who were instrumental to the completion of this project. Most importantly, Dr. Ulrenshaw for funding and giving us the opportunity to complete this. Dr. Brown for advising us throughout its completion, Dr. Christine Charstani for teaching us throughout the senior design courses, and various staff at FIU for helping us in the lab and for allowing us to use our facilities and equipment. With that, we'd like to thank you for listening to our presentation. And if you have any questions, feel free to reach out to us via email. Thank you.